今晚还没到我的地址，做好最后提醒1小时。12点半跟小伟一同编辑一个报告。为什么？4个小课任务。
Alright, let's get started. So I'm Dr. Paul Connolly. I'm a reader in the School of Earth and Environmental Science, and I'm taking over from Geraint's part of the course now for the rest of the semester. My focus is cloud physics. I'll be talking about the atmospheric physics part of the course and how that relates to meteorology, which is Geraint's part. I tend to focus more on the small scale physics, so micro scale up to cloud scale physics. Whereas Geraint's course, as you're aware, has focused more on the synoptic scale, synoptic to the global scale. That makes sense? So we're going to consider smaller scale physics now. I'm going to start off with something you covered before and then progress it a little bit further today. We want to think about how clouds form in the atmosphere. That's the first question. And think about what is a cloud at the microscopic level. Actually, can I just hand this around? Do you know what this is, by the way? Yeah. Swap that scanner. Let me just turn it on. Apparently there's something I need to scan in this room. So Geraint will have scanned it. Anyone know where it is? It's like a piece of paper with a barcode on it. Before I hand it to you. No? Give me 2 seconds. We'll do that later. Okay. So, some other questions to think about. How much water vapour can the air hold? Anyone thought about that physics, that branch of physics before? It's thermodynamics. Okay, so we'll be considering the second law of thermodynamics. And how does the air temperature affect how much water vapour the air can hold? You'll have thought about these things before, but we'll cover it in a bit more detail and relate that to cloud formation. Okay, so if we consider kinetic theory, which you're all physicists, well, some of you are, I think there's physicists and there's environmental scientists in here. You'll have thought about kinetic theory before. How does the speed or the kinetic energy of molecules affect their temperature? Okay, so that's fairly straightforward. There's a one-to-one relation. Faster the molecules move, the hotter they are. Okay, so you'll have all covered that before. And you do know laws describing how energy and work are related. Changing kinetic energy of a particle equals the work done. Yeah? You're familiar with that? So fairly basic to start off with. Now, I'm going to consider 2 boxes. There's a box here, and there's a small box here. And these 2 boxes contain molecules. And one of the boxes has fixed edges, so the walls can't move. And the other box, this small box, has flexible edges, so the walls can move. Okay? So what's going to happen when I start this animation is these gas molecules can rebound off the edges of the box. And that creates a steady pressure that you're all familiar with. You think about the molecules in this room, they bounce off the walls, they create a steady pressure on the walls. Okay. So what we're going to consider with this animation is the temperature of the gas in this box, the temperature of the gas. So we're going to go forward in time, and when we get to this point here, we're going to allow the gas molecules to do some work on the edges of the box and allow it to expand. So the box is going to expand, and we're going to see what happens to the temperature, and then at this point it's going to stop expanding and we'll see what happens to the temperature. Okay, so there the molecules are. They're bouncing around, creating that steady pressure on the sides of the box. Temperature's constant, temperature's constant. When we get to this point here, and we're going to allow the molecules to do some work on the sides of the box. And you can see what happens to the speed of the molecules when we allow that to happen. So they slow down. So therefore, the temperature goes down. Okay? We're all familiar with that. So these molecules are now slower than these molecules, and then we stop the box from expanding and the temperature remains constant. That's known as an adiabatic expansion. Okay, and I think Lorraine will have talked about that, but I'm going to talk about it again because it allows me to progress it a bit further. So we'll stop the presentation there and we'll just write something down, some equations. So where is it? Visualizer. Hopefully this works. Yeah. So this is a physics class, so we need to consider the quantitative aspects. So we start with the first law of thermodynamics. First law. So you'll have seen this before. du, that's the change in internal energy. Is the heat added to the system, Q. Minus the work done. Have you all seen that before? Anyone not seen that before? Okay. Work done. This is by the system. Now, if we consider 1 kilogram of air, think about a kilogram of air inside a container, maybe a balloon that can expand, and it's in the atmosphere. So that's an adiabatic parcel. There's no transfer of heat between the parcel and its surroundings. And in considering this parcel, we can consider how a cloud forms, the cloud formation process, which is the start of this course really. So, 1 kilogram of air. So this is a parcel. And air has a specific heat capacity of CV. That's defined as the specific heat capacity. Incidentally, I do have some notes that are on a web page which I'll send you all. I'll email you this web page after today's lecture. Okay, so that's the specific heat capacity. So change in internal energy, you all know, is CV times the change in temperature of the parcel. Yeah, you've seen that before. So Q is M times C times delta T, but this is for 1 kilogram of air, so M is 1. And that's equal to the heat added, dQ. Now the work done for this parcel, I'm going to write down, and then we'll think about it later, as minus P dV. Have you seen that before? Work done by a parcel. Has anyone not seen that before? Put your hand up if you've not seen it before. Everyone seems to have seen it. So it's in that case, I won't go through where it comes from. I'll just tell you that if we consider, I won't go through it in detail, if we consider this parcel which expands, so this is a balloon if you like, it expands by a certain amount, it has a pressure P, it changes its volume by delta V, and it has a surface area A, we could say, of this balloon. Then because work done equals F times dx, and delta V, if dx is small, delta V is A times dx, we can derive that the work done by this parcel is minus P dV. Is that okay? Good? Okay, so we'll call that equation 1. And Geraint might have gone through this too, but I'm going to progress it a little bit further. So let's consider the ideal gas law now. The ideal gas law, and I'm going to consider this for 1 kilogram of air. So not PV is nRT, but the different form that Geraint showed you, P is the density times the specific gas constant times temperature. PV equals RA times T. Now RA, I think Geraint has called R prime, but this is the RA is the specific gas constant for air. It's the universal gas constant divided by the molecular weight of air, and it works out to be, I'll try to define everything that I'm using, RA is 287 joules per Kelvin per kilogram, and V is the volume per kilogram. And so therefore, just rearrange, V equals RA over T over RAT over P. Just rearrange that. And if I differentiate that expression, that equation, differentiate, then I can write down dV equals P RA dt minus RA T. This is just using quotient rule, by the way. P squared. And we'll call that equation 2. So I've just differentiated this expression. So dV, if you think about it as u divided by v, v du by dx minus u dv by dx divided by v squared. Substitute 2 in 1. So substitute this equation 2 into this equation, and we'll end up with Cv dt dq minus Ra dt plus Rat over P dP. That's equation 3. So all I've done is just played around with the algebra there, substituted one equation into the other, and rearranged to find, so just gather like terms, the dt's can come together. Ra plus Cv dt equals dq plus Rat over P dP. Now there's a relation in thermodynamics called Mayer's relation. Have you heard about this? Doesn't matter. All it says is that, so this is Mayer's relation. All Mayer's relation says is that the specific heat at constant pressure minus the specific heat at constant volume, Cv, is equal to the specific gas constant. So this has been derived by a physicist called Mayer, which allows us to simplify this just a little bit. So we can write, I'll repeat this again, but it's fairly straightforward. Just substitute Cp in there. We'll call that equation 4. And it's an adiabatic expansion if there's no external source or sink of heat. So set dq to 0, and that's an adiabatic expansion. So we can derive, if that's the case, we derive dt by dp equals Rat over Cp times T. Now, if we consider this is the equation for an adiabatic parcel rising through the atmosphere and changing temperature as the pressure changes too. So we consider that parcel. We consider a parcel rising from T0, P0. So some temperature, some initial temperature, some initial pressure to T and P. Then we solve this differential equation and find that log T0 over T equals RA over CP. Log P0 over P. Or we can define a variable called the dry potential temperature. Dry potential temperature is if we set T0 equals to theta and P0 equal to 1000 hectopascal, then rearranging this equation we have theta equals T 1000 hectopascal over P to the power RA on CP. Okay, so this is a conserved quantity, which is why it's so important. So even in small scale processes, theta, the dry potential temperature, is conserved in the absence of moisture. So with dry air, heat is conserved. That means in convective processes, in processes that transport the air from one place to another, from one pressure to another, theta for that air will always be conserved. It's not conserved if we think about other processes, which we'll consider today. One of those processes is condensation. So this thing is not conserved. So considering cloud formation, where condensation happens, we need to consider another variable. It's also not conserved in radiative transfer processes. So the radiative transfer process is known as a diabatic process, whereas this is an adiabatic process. No transfer of heat. Have you seen that before? Some people saying yeah. Anyone not seen that before? So I think Geraint's shown that before. So try and make it a little bit more interesting. So this is a box like before, one of those boxes, and contains air molecules. So it contains various valves. There's a bike valve here, this one. There's a washing machine valve here, and it's basically a pressure sealed container. And there's a pressure relief valve here if the pressure gets too high, otherwise it's dangerous. So we're going to try and make a cloud by cooling the air, and the way we can cool the air is to first increase the pressure in here by pumping air into it and then letting the air out, decreasing the pressure very quickly. So it's that first process in the presentation, the one that we've been looking at, where air molecules inside, when I open this valve, will push against the surrounding molecules and do work against them, and so their temperature will decrease. So let's think about this a little bit. So I'm going to put some water in here, some liquid water. I'm going to close the container. Oops. Seal it up. Now what the liquid water does inside a sealed container is it will evaporate. It will evaporate until the water vapour above that liquid water is at what vapour pressure? It's at the saturation vapour pressure. So it's saturated. So if you leave it long enough, it will find an equilibrium where the water vapour pressure in here is at the saturation vapor pressure. Anyone not familiar with that term? Are you familiar with Clausius-Clapeyron? You heard about that? Clausius-Clapeyron. So Clausius-Clapeyron tells us that if we leave water in here, a condensed phase, then, because it's a sealed container, eventually what will happen is some evaporation until above this water surface is at water saturation. So it's pretty close to saturation, and then if it's at saturation, if we cool the gas a little bit further, then we should get some condensation. Yeah? So I'm going to try and cool it by the method I've just talked about. I'm going to increase the pressure in here. 25 pumps does it. So it's about 1.3 atmospheres in there now. And then if I let the air out, the air should do some work against the surroundings. Oh, nothing happened, did it? Okay, and the reason why nothing happens, this is an important point. Does anyone know? What do we need to make a cloud? What's missing? Say again?
Cloud condensation nuclei.
Cloud condensation nuclei, yeah, we've done this before. Cloud condensation nuclei. I'm going to make some cloud condensation nuclei using a map. So cloud condensation nuclei, small particles. They're small particles, we call them aerosol particles, okay? And they're in the atmosphere, and cloud condensation nuclei are a subset of the aerosol particles. So that means that not all aerosol particles can act as cloud condensation nuclei. It turns out you burn a piece of wood, then you get lots of cloud condensation nuclei. We'll try that now. Don't want to spill it. Not working. Bear with me 1 second. Okay, so burning this piece of wood is generating billions of small cloud condensation nuclei, and I hope I don't burn my finger. So we've got some smoke particles in there now, and we'll repeat the experiment. So close it up. 25 pumps does it. It's leaking a bit. Close it up. So exactly the same experiment before, but with cloud condensation nuclei. You see that? So you can see the cloud. Now, the other interesting thing, if I increase the pressure in there, do you notice anything there? You see that? So you should have seen that the cloud evaporated. Okay, so think about low pressure as being responsible for cloud formation processes. Think about high pressure as being the opposite. So if the weather is high pressure, you tend not to see high clouds in the atmosphere or mid-level clouds. If it's low pressure, you'll see more clouds and rain and so on. And over the next week or so, we've got low pressure. Surprise, surprise. There we go again. Okay, so let's just go back to the presentation. So warm air holds more water vapour than cold air. This is described by the Clausius-Clapeyron equation. You know this because if you park your car on a cold night and there's some water vapour inside the car, and if it's cold, if it's warm, in the evening and colder through the night, by the morning you've got some condensation on the windows. So the amount of water vapour that the air can hold is described by a relation that looks like this. It changes with temperature, and what it means is, so this is the amount of water that air can hold. It's also known as the saturation vapour pressure, measured in pascals. It means if the vapour pressure of water is below this line, then the water will be water vapour. If the total water is above this line, then you'll have water vapour plus condensed water at equilibrium. So water vapour exists there. Water exists as liquid and vapour here. Even at low temperatures, we can also have ice if the temperature is low enough. So it could be condensed. When I say condensed, I mean liquid. I also mean ice too. Condensed to solid. So if you've got this much water in the air in your car, and if it cools overnight, you cross that line and you get some condensation on the windows, maybe even some ice on the windows. Okay, so we've also talked about cloud condensation nuclei, also referred to as CCN, that's the acronym. And basically our little cloud chamber experiment showed that we needed these inside the chamber to make a cloud. So the water vapour needs some site to condense onto, and if it doesn't, then we can't see the cloud. The reason why we see the cloud is just because the light travelling through that chamber scatters the cloud particles scatter the light, and it makes it appear white. Okay, so basically we needed the cloud condensation nuclei. So here's a box with cloud condensation nuclei in it. Once we cross that line, they grow. Some of them grow, not all of the aerosol particles grow. So we needed 7 steps to make a cloud. We needed to close the large valve on the chamber, open the screw cap, put some water in the chamber, strike a match, blow it out, put it in, close the cap again, pump air into it, and open the large valve. When we open the large valve, what's happening is the air in that chamber is doing work against the surrounding air, so the temperature goes down. So the key point here is that the thermodynamics of air are important. When I talk about the thermodynamics, I mean this relation between pressure and temperature, but we also need particles in the atmosphere. We also need the particles. Okay, so just to progress that a little bit further, I get confused with this thing. Visualizer display. So I'm guessing you've seen the equation for potential temperature before, this relation. So the only difference when we consider condensation, the only real difference is starting with equation 4 here, there's a source of heat, which is the latent heat of condensation. So we start with equation 4, write it down again. Cp dt equals, so Ra dp P, and add on the additional latent heat of condensation, so that would be what I'm calling the latent heat of vaporization times the change in liquid water mixing ratio. So WL is what I call the liquid water mixing ratio. It's the mass of liquid water per unit mass of air, kilograms per kilogram. So in this equation here, LV is the latent heat of vaporization, and that's equal to about 2.5 times 10 to the 6 joules per kilogram. Means that you condense a kilogram, then it releases 2.5 times 10 to the 6 joules. WL is the liquid water mixing ratio. If the air is saturated, we can also write this down as same thing, except for the last term we can write down as minus LV dWs. WS is the saturation vapor mixing ratio. So it's an adiabatic parcel in that the water is conserved in the parcel. So we've got water vapour and we've got liquid water. Condensation of water implies that the water vapour goes into that water. So +1 means minus the other, if that makes sense. And using that last equation, you can choose initial temperature T0, initial pressure P0 equals 1000 hectopascals, and write down another equation. It's the moist potential temperature, theta Q sat, I'm calling it. Looks quite similar to the potential temperature. But there's this additional term, exponential term. Okay, so that's the final thing. Now the important thing about theta Q sat, so we considered a dry adiabatic process. Well, in a moist adiabatic process, so in that cloud chamber when we had a cloud, theta Q sat will be conserved. So theta Q sat is conserved during a moist, meaning there's water in the parcel, adiabatic process. Okay. That means that if we start with the initial temperature and pressure in my cloud chamber and it's at water saturation, I can calculate theta Q sat for the initial conditions. After the expansion, when I open the valve, the temperature inside's changed, the pressure's changed because I've let the air out, and there's now a cloud. So the saturation vapor mixing ratio has changed too. If I calculate theta Q sat, they should be the same, they should be equivalent. So that means if I know the final pressure and I know the final temperature, I should be able to calculate the mixing ratio of cloud using those terms. Maybe up to. Does that make sense? Okay. I just want to define one thing that I've not really defined properly. So it's just a small definition, in that this vapor mixing ratio, I'll call it WV for vapor, the mixing ratio of vapor, is the number of kilograms of water vapor per kilogram of air. It's the way we quantify how much water vapor there is in the air. And so in order to arrive at the definition we use, so this is measured in kilograms per kilogram. So I can start with the ideal gas law for vapor. And so the ideal gas law for vapor, I'll call the vapor pressure E, V, and I'll call the vapor density rho, V, and we've got the specific gas constant for air, RV and T. You've seen this before. So Geraint's talks about this form of the ideal gas law. So it's a pressure is equal to a density times a gas constant times temperature. So this is for vapour. And similarly for the air, we've got the pressure, which we call P, and we've got the air density, I'll call it rho A, and the specific gas constant for air, Ra, and temperature. Divide one by the other, so divide this equation by this equation, and we're left with EV over P equals rho V over rho A, RV over RA, and the temperatures cancel because it's in the same mass of air, so we assume it's well mixed. So these two temperatures cancel. Now, if we think about rho V, that's the kilograms of water vapour per metre cubed, and if we think about rho A, that's the kilograms of air per metre cubed. So divide one by the other, it's all in metre cubed. We've got the kilograms of water vapour per kilogram of air, and that's the mixing ratio I want. So just rearrange for that. We have WV equals rho V over rho A, and that's equal to RA over RV, EV over P. So my mixing ratio is RA over RV, E over P. That means the mixing ratio of water vapour is this ratio of the two specific gas constants, which works out to be about 0.62, multiplied by the vapour pressure of water, divided by the total pressure. Okay, so that's just the definition, but it's useful to see where that comes from. Now, just finally, this is where I bring it together a little bit. So if we wanted to, if we're considering a parcel of air at the surface, so there's the ground, there's a person at the surface, and he measures the temperature and the pressure and the water vapour mixing ratio in this parcel. Okay. Now this parcel rises up through the boundary layer in a thermal and condenses when it gets to cloud base. So this is cloud base. And what usually happens, it gets to cloud top. This is cloud top. Stops there and eventually starts to sink. And that happens continually for lots of different parcels. Lots of different parcels. And this is a good approximation for calculating the cloud properties in very thin clouds, which is why we're considering it. So very thin clouds, which are called stratus clouds. So how could I calculate how much liquid water is at cloud top? Well, what you do is you calculate the dry potential temperature, theta, and actually no, you calculate the moist potential temperature, theta q sat, and then at cloud base you calculate theta q sat again. Well, you wouldn't have to calculate it because it'd be conserved, so it's the same, but that would allow you to calculate the temperature and the pressure at cloud base, and then at cloud top you calculate theta q sat again, and that would allow you to calculate the temperature and the pressure of cloud top. Okay? But if we wanted to calculate the liquid water content, how do we do that? Well, we could do it like this. So if we knew the temperature and the pressure at cloud base, we could then calculate the saturated vapor mixing ratio at cloud base. So how much water vapor is at cloud base? Okay, and for conditions of saturation, so that's known as Ws, using the equation that I showed you previously, just derived it. And we could do the same at cloud top, so Ws, so I'll call this T, and I'll call this B, the cloud base. So if I know how much water vapour there is here at cloud base, and if I know how much water vapour there is at cloud top, how can I calculate the liquid water content in the cloud? I've been talking for a while, so I said a few things, but have a think about how you do that. So we're considering that the parcel's adiabatic. So there's no transfer of water in and out of this parcel with air. Water substance is conserved. That means if you take the water vapour and the liquid water, add them together, it will always be the same for this parcel. So how do you think I would calculate how much liquid water is condensed? I know the temperature and pressure at both cloud base and cloud top. Anyone? Now the saturation vapor mixing ratio, and calculate that from temperature and pressure. I confused you, I think. Alright, so a related question. At cloud base, if you think about the saturation vapor mixing ratio at cloud base, is that higher than at cloud top or lower? So in other words, can the air hold more water vapor at cloud base or at cloud top? Can it hold more or less? Anyone want to try and say? No one wants to try?
More.
More at cloud base?
Yeah.
Yes, it holds more water vapour at cloud base. Why, primarily?
It'd be from a really, it'd be warmer.
It's warmer, yeah, of course. That's it. Okay, so it's warmer at cloud base, so the air can hold more water vapour. So the saturation vapor mixing ratio is higher or lower?
Higher.
Higher, yeah. So we've got saturation vapor mixing ratio at cloud base. We've got saturation vapor mixing ratio at cloud top, which is lower. How can I calculate the liquid water content, the liquid water, condensed water? It's really easy.
Find the difference between the two.
Just the difference between the two. Yeah. Take one from the other. Take which one away from which? Again, it's obvious. Anyone want to say?
Base from the top.
The base from the top, yeah. The highest from the lowest tells us the liquid water. If we do that at every level in the cloud, it will tell us the profile of liquid water. So that's known as the adiabatic liquid water mixing ratio. So it's the saturation vapor pressure at base, at cloud base, so this is a function, minus the saturation vapor mixing ratio at cloud top conditions. That tells us the amount of condensed liquid water in this cloud. The reason why I've gone through that is because it's a really good approximation. For stratus clouds, it's really is really accurate to do this. So we can learn something about stratus clouds by looking at this quantity. When the clouds get a bit deeper, as we'll find, this doesn't really work, and that's because we have precipitation, we have rain formation, we might have ice clouds, and we also start to have mixing between the clear air above cloud top and the cloudy air. So it no longer becomes a good approximation. So adiabatic liquid water mixing ratio is a good approximation for what we call boundary layer clouds, which are usually at the top of the atmosphere that we call the boundary layer, which is usually the lowest 1 kilometre in the atmosphere, and when the clouds are typically less than about 200 metres thick. So that refers to stratus clouds or stratocumulus clouds. And I'll show you some examples next lecture, but just to finish off, I don't want to press the wrong button. Okay, yeah. Just to finish off, let's think about, I've got a minute or two, let's think about how the number of cloud condensation nuclei affects how much sunlight is reflected. So when we think about the liquid water content in a cloud, okay, the amount of liquid water content, that's governed by the thermodynamics. So regardless of how many aerosol particles you have, how many CCM, cloud condensation nuclei you have, the cloud water content in these thin clouds will always be pretty much the same. So we can calculate that through thermodynamic considerations like we've done. But it is important, aerosol particles are important to how much sunlight is reflected. And this is just like a toy example. So basically this example is supposed to be looking down over an ocean with a cloud in the way. So the circle's a cloud because they're white. No. And we just increase the number of aerosol particles. So the size of these cloud droplets decreases. But the total volume, if we retard at the total volume, it remains the same. So when we really increase the number of aerosol particles, they get much smaller. But the average colour, if you just sort of squint your eyes, the average colour as you go from left to right goes more white. So there's basically more scattering of light as we go from left to right, which means that the clouds reflect more solar radiation. And that's one of the things that the IPCC, the Intergovernmental Panel on Climate Change, look at. They look at what we call the radiative forcing of clouds, and what they're saying is since pre-industrial times, when the aerosol particle concentrations were low, what change have humans made by adding aerosol particles through combustion processes and so on to the cloud effect? And it's about -1 watts per metre squared on average. So clouds on average cool the Earth by about -1 watt per metre squared. So actually the additional effect that humans have added is about -1 watt per metre squared. Does that make sense? So the aerosol particles that humans have added is about -1 watt per metre squared. That's all I wanted to say. We'll pick that up next lecture, and I will send you out the web page with all the PowerPoints and everything for the rest of the semester. Okay, thank you. In terms of scanning swipe cards, I can't find it, so we're going to have to leave it unless you can find it now. But